To do this one algebraically, we need to raise 2 plus x to the third power. I'm going to get some help from Pascal's triangle. So this is going to be 1 times 2 to the third times x to the 0th plus 3 times 2 to the second times x to the first plus 3 times 2 to the first times x to the second plus 1 times 2 to the 0th times x to the third. So this is 8 plus 12x plus 6x squared plus x cubed. Hopefully you notice that the 8s are going to cancel out. And then once we have canceled the 8s out, everything left in this problem, in this argument, has an x in it. So we will cancel the x out. So we have, the argument is 12 plus 6x plus x squared. Remember, the easiest way to evaluate a limit is substitution. As x goes to 0, this is 12 plus 0 plus 0. So the limit is 12. You could do substitution in the beginning, but you would get 0 over 0, so substitution wasn't helpful. Now let me show you the graph of this argument, because we should be able to get this answer graphically as well. Here's the graph with zoom fit, and when we trace 0, you notice there's not a y value showing up. So I'm going to go to table set, start at 0, and let it change by 0.01. When I go to the table, we can get a pretty good idea that it is approaching 12. We could go back to table setup, let it change by 0.001, see if we can get even more evidence. It's getting very close to 12 as x gets close to 0. Okay, number 29 is a problem we are supposed to show graphically why the limit doesn't exist. So we could just graph the argument in the calculator, but with this simple rational function, we can also do it by hand. Remember, when the bottom is equal to 0, you're going to have a vertical asymptote. So that's at x equals 1. When the numerator is equal to 0, you're going to have x-intercepts. So that's at positive 2 and negative 2. This one doesn't have any holes because there's not any factor common to the top and bottom. With one more point, we can really figure out what's going on at this vertical asymptote. We can find the y-intercept by plugging 0 in for x. So that would be negative 4 over negative 1, and that's going to give us a y-intercept of positive 4. Well, actually, to make sure we know what happens on this side, maybe we should plug in one more point. Maybe x equals 3. So that'd be 5 halves. So at 3, we're up at 2.5. So the graph should look like that. Confirm it with your graphing calculator, but this shows that the limit as x approaches 1 does not exist, because the limit from the left side goes to infinity, and the limit from the right side goes to negative infinity. Number 63. To find the average velocity during the first 3 seconds, we need to find y of 3, y of 0, and we'll divide that by 3 minus 0. Plugging 3 in, I already did this, I got 44.1. Plugging 0 in, you get 0. So this is 44.1 over 3, which is 14.7. Now this was measured in meters per per second. So that'll be the units on our answer. The example we did in class, I believe, was in feet per second. That's why we had a different number out front. To find the instantaneous velocity at 3 seconds in, we need to use a limit of our difference quotient, looking at two very close points, 3 and 3 plus h. As h goes to 0, these 2 points become closer and closer, so that the average velocity approaches the instantaneous velocity. Need to plug 3 plus h in for t. Let's see, if we're squaring 3 plus h, I think that'll give us 9 plus 6h plus h squared. We already know what we get when we plug 3 in. We did that. That was 44.1. And I'm going to go ahead and cancel those out. Our denominator is just h. Need to distribute a 4.9. Let's see, 45, I think maybe 44.1. No surprise there, same number as that. That'll cancel out. Let's see, 29.4, I think. I should have done this beforehand so that I would know. Alright, so 44.1s cancel out. Let's carry this up here. We're left with 29.4 h plus 4.9 h squared all over h. Notice that everything in the argument at this point has an h in it. And the easiest way to evaluate a limit is substitution. We'll do that now. Seems like the instantaneous velocity 3 seconds in is 29.4 meters per second. I hope you found this helpful. Stay warm and safe today, and hopefully we'll all be back here tomorrow.